Alright, good morning everyone. Let's start with the quiz 8. Okay, how many were you able to calculate these receptive fields? Sorry? That's fine. 4 cross 4, 4 star 4, all of that, all of those are. Yeah, that's fine. How many were able to calculate this? Let's see that. The answer was not wrong. Yeah, because I tried to add many different variations, but you guys still beat me. I did 4 cross 4, 4 star 4 and others, but one space, because comparing strings, so I would have missed the string which you mentioned. So I'll have to manually go there and edit that. Okay, so let's look at this network. Input is 64, 64. In convolution 32, 3 cross 3 padding to stride 2, max filling and all. The final receptive field network is, basically we're trying to calculate the final receptive field here. So what is the step, what should I do? Right? So okay, so first let's write my input resolution. So I'll say here input, then output, then this is receptive field, then this is my jump in. Okay, so my input resolution is, doesn't matter actually. Okay, first we are doing 32 and then stride of 2 and then padding of 2, right? We are writing kernel, padding and stride. Now input resolution is 64, output resolution is what? 64 plus 2 into 2 minus 3 divided by 1 plus 1. Yes, no? Good morning. Yes, no? Good morning. Yes or no? Stride is 2. Good morning. Okay, so this is 1, 65 divided by 2, 65 divided by 2 is 32 plus 1, 33. Okay, receptive field, jump in is what? 1. What is the first thing we are going to do now? Convert a jump into 2. So receptive field right now is going to be 1 plus kernel size minus 1 into jump. This becomes 3. Alright, what is the next step? Max pulling with a stride of 2. Jumping up becomes 4. 33. 33 plus 2 into padding minus kernel size divided by 2 plus 1 is gone. 31. 15 plus 1, 16. Receptive field is now 3 plus 3 minus 1 into 2, right? So 3 plus 4, 7. Now what is the next step? This done, this left. So we are saying 5 and then 2 and 2. Now this becomes 8 immediately. This is 16. 16 plus 2 into 2 minus 5 divided by 2 plus 1 minus 1, 15, 7, 8. This becomes 8. Receptive field is what? 7 plus 5 minus 1 multiplied by 4. So this is 16. 16 plus 7, 23. What is the next step? Max pooling, which is MP stride of 2. 8, this is 4. 16, then 23 plus 2 minus 1 into jump, right? So 23 plus 8 is 31. Any question on this? Yes, no?
Dhruvan, in the first step, we have a 32, that is a number of channels, right? Then styles 2 and padding 2, right?
That's correct.
But in the here you have it is 32 5 by 5. This 5 and 5 is a kernel. Then 32 should be the channels in the second last step.
Yeah, this is not required. This is 3.
Okay.
Have you done any mistake here? Sorry? Divide by stride? Which one? Yeah, this is receptive field. Yes, no, any? Okay, so for the question we're asking receptive field, that's 29, and we are asking final output channel 4 cross 4, then we're asking final value of J is 16, right? What did we get? Oh, great. We got 31 here. What is the wrong step we did? We did max pulling here. What did we do? So 3 plus 2 minus 1 into 2. So this is should be plus 2. So this is not 7. This is 5. Then this is not 23. This is 21. This is not 31. This is 29. Okay. Now, which of the following is true? It is advisable to add max filling just before prediction. No, definitely no, right? We will not. We'll never want to do that. It is advisable to not use BN before the prediction layer. That is true. Just before the prediction layer, you are not supposed to do anything. Object detection network can have dilated kernels, right? Okay. Softmax probabilities are directly proportional to the object feature found in the image. Not true, right? They're exponentially related. There's no linear relationship there. It's an exponential relationship. Dilated kernel, we covered that in our, so let's say, currently when you're convolving, you're going to convolve with this kernel. You're going to convolve these 9, right? Yes, no? But when you use dilated kernel, what happens? You're going to be using this one, this one, and this one, this one, this one, and this one, this one, this one, this one. Remember that octopus kernel? That's the dilated kernel.
Softmax is still, I mean, when we use softmax, even though it's exponential, it's still directly proportional, right?
No. Proportionality is linked to the power. For example, there's a square law. We call it a square law because it's linked to the square of.
Oh, yeah, 100%.
Yes. Okay. Now, one PhD student has written a network to localize the object in an image without training on the object localization data. He has used following classification data. Basically, you have only images of dogs, but it does not say exactly where the dog is inside the image. And this is something you're going to face as in your career also, that you will have a problem where you want to create bonding boxes around objects, but you don't have time to sit and make those bonding boxes. Right? There's a client which is asking you to create a demo within a week. You have a data set and you don't want to sit through and make those bonding boxes. What are you going to do? That's what we are asking here. Now, what all he must have done. Now, you are going to avoid any fully connected layer in your network, right? The moment you add any fully connected layer, and we are talking about before your global average pooling. If you add any fully connected layer before global average pooling, you're going to be converting your 1D, 2D into 1D. You're going to be flatten your data. As soon as you flatten your data, your 2D information is gone. So there is no bonding box information which you can extract even if you wanted to. Kept the resolution of the prediction layer high. Do you understand this part? Kept the resolution of the prediction layer high, which means that you will not go to 3 cross 3. If you go to 3 cross 3, you can only say which block your object is in. You'll need to have a higher area of the output image, so you can say that my object precisely belongs in this particular area. Equal to the size of the. Not equal. If you do equal, then it becomes very difficult to train a network also. So that feature map will contain multiple templates. Sorry, repeat that. That feature multiple multiple templates. That is receptive field. What we are talking about here is a prediction layer resolution. Image segmentation we do. Image segmentation is different. This is bonding box prediction. So image segmentation, you really need a one-on-one mapping. So if this is your image, you really want to have this kind of mapping. But the problem we are discussing is object detection. So in object detection, it is good that you have just, let's say, a bonding box around that. So this is good enough for us. Right? So what happens in object detection is that this is your prediction layer. You're not going to be predicting now 10 numbers. You're going to be predicting a full, very big channel. So if let's see what happens in YOLO, you will get some idea. So input is 224 cross 224. That is the size of the images which comes in. We add a VGG16 in between. So this goes through VGG16, and finally we have around 13 cross 13 channels. Right? So what we are going to do basically, we are going to take our image. We are going to divide our image in 13 cross 13. I'm not drawing 13 cross 13 here, but imagine these are 13 cross 13. Correct? And now if let's say we have an object here. All of these bonding boxes are going to fire. Basically the channel you are going to have, there you will have ones here, or numbers which are very high here, and where the object is not there, you will have zeros there. Right? So what is going to happen, each one of them are going to predict some sort of bonding box. So this guy is going to predict a bonding box, this guy is going to predict a bonding box, everyone is going to predict a bonding box. So based on how your data is structured in the image, so this specific guy will give you a bonding box like that. This guy will give you a bonding box like this, depending on how your objects are centered. So what is going to happen, many bonding boxes are going to be predicted. And finally we take a sum of this, and that sum or that average of these bonding boxes, there's something called non-maximum separation which we are going to see. But when you do non-maximum separation, essentially you're going to get a bonding box which looks like that. So what is going to happen is your 13 cross 13 actually looks like 13 cross 13 cross 5 cross 125. Right? So this 13 cross 13 actually has depth. And this we just said 13 cross 5 cross 125. So this is 4D. So let's forget about 125 for a while. Let's look at only the 5 guy. So this is going to be divided into 5 boxes. Right? And these 5 boxes, so 13 cross 13 is a channel, resolution. So 1, 2, 3, 4, 5 in X and Y axis. And this 5 is what? X, Y, H, W and C. X, Y tells us the centroid of the bonding box. This is the X and Y. Where exactly is my X and Y? H and W is the height and width of the bonding box. And C is that parameter we're talking about, whether it's 0 or 1. So C is going to be 1, where if this is going to be 1, but this is going to be 0. C is the objectness, whether I have a class or not. Only thing it's going to say is that whether I have a class or not. So our 13 cross 13 cross 5 cross 125. These are the resolution. These are the channel resolution. So this is 13 cross 13 resolution. 5 is the how many channels I'm getting. And this channel is going to be your X. So the way it predicts is, this is 13 cross 13, right? And inside 13 cross 13, let's say we're talking about this particular cell. X and Y is this axis, this X and this Y. So with respect to the bonding box, what is the X and what is the Y? And this is 0 and this is 1. So what is the maximum possible here? 1, 1. So we are interested in knowing exactly where is the point, where is the centroid of the bonding box inside that cell. Right? We are interested in knowing where is the centroid of the bonding box inside that cell. So let's say this guy tells us that my centroid is at, give me some values of centroid. Some other value? 0.2, 0.9. Some other value? Not possible. That's why I'm asking for some value. I just said this is limited to 0 and 1, 0 and 1. We are going to use a sigmoid here, which is going to squish all the values which are going to come in between 0 and 1. So tell me any other value? That is possible. Root, you said root 2? Yeah, that is possible. Point 2. What are the values which are not possible? 3, 4, minus 1, those values are not possible, right? Because we are looking at 0 and 1, 0 and 1. So you're going to get a value somewhere inside that. Let's say that the dot which I made is the value. So that this channel is just going to just store this x value. So let's say this is going to be 0.2. This channel is going to store, let's say 0.3. So this is 0.2 and 0.3. Now this channel is going to store h and this channel is going to store w. What is h and w? Height and width of the bonding box, right? What is the maximum height possible? 13. What is the maximum width possible? 13. Why 13? Our image is divided into 13 boxes. So it's going to be a fraction of this 13. So it's going to tell us with respect to the image, what is the height of my bonding box, what is the width of my bonding box. So we're going to get something like this. But this is the most important channel, and this channel is called objectness. That tells us whether there is an object or not. So you're going to be training this whole network on classes, yes, but you're also going to be training this network on predicting whether there is an object or not. And this does not concern about what object are we talking about. This may be a car, this may be a face, this may literally be anything. So this parameter is going to say whether I have an object or not. If this has an object, then this is going to be 1 or very close to 1, and values which are close to 1 are the only values which you check. So we don't have to check x and y and h and w for every single 13 cross 13. We're only going to check C first. So if C says I have an object, we are going to be only checking that. So first thing what we do, we sort the whole 13 cross 13, 169 values of C channel and see which is the highest one. The one which has the highest is looking at the object with the most highest receptive field. Like the largest coverage for that particular pixel is going to be for that particular cell which is looking exactly on top. So we are going to, but that still limits us to checking around 2 to 3 cells. I drew many more in the last image, but we checked 2 or 3 cells which are at the highest class objectness parameter. So right now this guy is telling us that I have 1. So we are going to be looking at this. This is telling us x and y and h and w. And then we have 125 for 125 classes. So you have 5 is number of channels here. 1, 2, 3, 4, 5. Let's say 5 cross 20. Yeah, okay. This is 13 cross 13, right? This is now 13 cross 13, 13 cross 13 cross 1, right? I've just drawn 1, 13 cross 13 cross 1, and this, if I make this 1, I have what? 20. What does 20 mean? I have 20 channels inside, right? Let's keep it very simple. 2, right? And this was what? 5. So if I keep this as 5, I can redraw it. See, this is 4 dimension, so we are manipulating at 2 dimensions to make sure we can still work with 4 dimensions. This is, what is the size of this? 13 cross 13. What is this? 5, which means I have to divide this into 5. 1, 2, 3, 4, 5. This is 13 cross 5, and then we are saying 2. So what we are saying essentially is that each one of them are 2. Right? This is cat, this is dog, this is cat, this is dog, this is cat, dog, cat and dog, and cat and dog.
Basically the number of classes there.
Number of classes. So if you had 20 classes here, I will have to have 20 structures inside.
And they will be some kind of one hot counting that.
Yeah. But see, I've converted, manipulating my 3D into 2D. So you're going to imagine that C and D is again a 13 cross 13 number. That's not. It's just one single digit, right? What you need to realize that what we're saying 13 cross 5 cross 20, 20, right? So the kind of predictions you're going to get is going to be for 13 cross 13. You have this full channel. In that, let's say this is the one which is saying my objectness is 1, right? This is going to predict x, y, h and w, and that inside will have 20 cells. This is softmax, so only one can be one. Each cell can predict only one class.
This is for label data, right?
This for?
While training, we need to feed label data in this.
Where
This.
objectness is one, so where objectness is one, only those values will, those places we will have values for x and y.
Yes. Yes.
So is this the output layer? This is not the output layer. Is this one layer before the output
This
layer?
is the output layer.
No, no, but if there are two objects which are very close, then you know which one. Okay, it's softmax, it has probability will.
See, if two objects are very close to each other, you can only see one.
No, it's objectness.
Object is.
Objectness. Okay, one means there is an object, so it doesn't matter.
Yeah. Inside that, the inside that you're going to go and check whether this is a cat or a dog. Now, what we are just checking, what we are discussing right now is YOLO V1. In YOLO V1, the problem was that we had only few templates, so we were forcing each bonding box to predict what template what is the bonding box, right? What you saw that first thing, right? This 5, we were predicting X, Y, H, and W. Now, this is a very difficult task because each cell now has to figure out the range of prediction of bonding boxes now can be very small to very large, and that is something which is very difficult for the network. So in the second model, what happened is your 13 cross 13, we had this 5 here, but this 5, let me pick another number. Let me pick, let's say 3 here, and then 25. So in the second model, what happened? This 3, instead of becoming my X and Y and H and W, became the template. So I had template 1, I had template 2, and I had template 3. Basically, template 1, which is going to be a square, so it's going to predict objects which are squarish. Template 2, which is going to be a longer rectangle, and template 3, which is going to predict.
These are the shape of anchors.
These are the shape of the anchor boxes. These are called anchor boxes. So we have 5 anchor boxes in our YOLO.
So loss will be regression loss plus classification.
Yes. So what is going to happen now? Instead of predicting what directly X, Y, H, and W, we are going to have 5 different predictions. Each one of them is going to predict whether I have an object or not, right? And where do we pass on that variable now? We pass on that variable in 25. So in 25, we have 20 classes and the same 5 parameters we spoke about. So you're going to have X and Y and H and W and objectness. So the algorithm still remains the same. What we are going to do, we are first going to check what? C. Wherever we have the C, then we are going to do what? Check the templates. Each template has these predictions, these C predictions, right? We have 13 cross 13 cross 5 because we have cross 5, which means each one will have a C. Yes, no?
Yes.
100% yes?
Yes.
Yes, right? Now what is happening is this guy has a C which is equal to 1. This guy has a C which is equal to 1. Now what can happen is I can check, I got this my X, Y, H and W from my this particular template, let's say template number 5. Is that correct? Then I'm going to check which class are you talking about. And then what this template can tell me that, oh, this is a man. So this template is seeing a man. But when I go to this guy, template number 3, that has also a very high value for the C. When I go and check inside, what exactly are you? That guy is telling me what? A car. This is how we do multi-object even if they are overlapping. Because we can go to a template, each cell can now predict at max 5 different classes, right? I could be predicting a cat and a dog, but they have to be, the overlap has to be different. That is why we use different templates. If two objects are using exactly the same template, then they are not visible. They are literally overlapping each other.
So Rohan, in normal architecture, we suppose before the output layer, we create 128 channels, the way we superposition channels.
Before output layer, this is the output layer.
Yes. Before output layer, we create, suppose, till the end of the skip field, 128 channels. How we are translating from, and the size might be 13 cross 13. From 128 channels, how we are translating to output layer?
You are asking a NumPy question. It's literally a NumPy problem. It's literally a reshape problem.
Why am I asking? Because we know 128 channels are different channels. Here, 5 is a channel.
First in YOLO, you're going to go to 1024 channels. And then you're going to take that 13 cross 13 1024 channel, repurpose them into 13 cross 13 cross 5 cross 125 or 25. That is literally a NumPy problem. There's nothing special there. But as soon as you rearrange, you're going to be connecting it to the number of parameters you have, basically your data, your label, and because that is how we actually train. right? So how your data is going to look like when this is your image and this is a man. How are you going to create your data? First, we are going to divide the image into 13 blocks, right? Let's say this is the block in which my object fell. Centroid. We are going to take that particular centroid. So we are going to create a JSON or a kind of label file where in 13 cross 13, how many boxes I have? 169. 168 boxes I have 0 as a objectness. Only one cell has objectness equal to 1. Is that correct? Let's say that.
Multiple cells, right?
Sorry?
There could be multiple cells.
The centroid of the bonding box will fall only in one of the cell.
Okay, yeah.
So the cell we are picking is where the centroid of the bonding box is falling. Now that part is going to be what? Let's say 5, 4. Right? So out of 13 cross 13, I've picked first values 5, 4. Now what is the second value? 13 cross 13 cross 5. So I need to pick which template are we talking about. Right now the template which I'm going to draw looks like that. Which template is this? This is template number 5. So this is going to be 5. Right? Now
Four is the first point. What is 5,4?
the which box is this? 13. We have 13, 13.
Right.
Which box are we talking about? I'm talking about 5, 4 box.
Okay.
Right? And then what is left? 25. So in 25, what are the first 20?
The classes.
The classes. So we are going to say man. So this is going to be 1. This is your hot vector.
You should also have the size before.
Sorry?
You also have the size before.
Not done yet. So this is 20. And then what is left? These 5. What are these 5? 1, 2, 3, 4, 5. This is what? X. This is what? Y. This is what? H. This is what? W. And this is what? Classness. Right? Now X and Y remain same. That is going to be in, this is one cell we are looking out from 13 cross 13. Inside this, how big is my X and how big is my Y? Again limiting to 1, 1. Now what is H and what is W? This is a scale parameter of your template. Let's say you had a longer template but you are looking at a snake. Snake will have even longer template. So it will have a higher height multiplier and maybe a smaller width multiplier. So your width is going to become smaller. Yeah? So if you want to convert this into something like this, you'll have to multiply your height with some bigger number. And what is a C? C is the classness. So it's a very introductory level understanding of how you're going to label your data, but this is what you're going to store and everything else is going to be 0. You have to store how many values per image? 13 cross 13 cross 5 cross 20. You have to store those many values. Right? So your data is simply going to look like 0, 0, 0, 0, 0, 0 and finally for that cell 5, 4. So this is 0, 0 cell, right? All the values are 0. This is 0, 1 cell, all the values are 0. This is 0, 13 cell, we have some 12th cell, this is all 0, 0, right? All 0, 0 till your 4, 5 cell. In the 4, 5 cell, what is the first value? We have 5 templates. In the 5 template, we have 1 here and we have zeros here, right? In this one template, how many values I have? 25 values. So in 25 values, I'm going to store my X, I'm going to store my Y, I'm going to store my H, I'm going to store my W, I'm going to store my C, and I'm going to store which class this is, man. And this is also what? One hot vector. So this is 0, 0, 0, 1, 0, 0, 0. How do we train a model? We first train a model on this classification, whether the image has a man, whether the image has a dog, and this is only one image, one object per image. Because if you do not know how an object looks like, how can you ask about a bonding box? So we train slowly. So we train for this and we also train for objectness, which is this one. This was a template, right? So along with the template, I will have this objectness variable, C variable, sorry, the C variable. So we train for both. We train for the objectness and we train for the object.
C template, right? 1, 2, 3, 4, 5, which that is C, right?
No, this is template. That template is saying 1. In that template, you have that C. That C is 1. So you're going to check all the C's first.
Log 1 is the C, right? Man, the 0, 0, 1. At 3, the man is there. What is the C then?
Objectness, whether there's an object, whether there's an object or not.
So we'll go to centroid of every object and then we'll feed data, right?
Yes. So this is how you're going to store your data.
Values
Why
of
don't you remove all those and just use 4, wherever the centroids are?
That's what we've done. We've just mentioned 0. You still have to mention 0 because when you're comparing a loss function, you're going to predict something, that minus something has to be there. So it's just going to be 0. We just stored this actually. We don't have to store all.
Loss functions for classification and XY, CW all
Yes, there are three loss function which you're going to combine, and you're going to first is was classification loss, right? First is classification plus soft localization loss. What is soft localization? Your objectness. See what we have done here. As soon as we say that this cell has an object, you have already identified the location, right? For example, this is a terrorist and you are just beating the hell out of him. You have made him say Indranagar. The moment you have forced him to say Indranagar, a big amount of localization is done. Out of whole India, we are not saying 13 cross under 13 cross 13. My object is at cell 4,5. Now you're going to, once this is trained properly, then you're going to train the rest of the components, where you're going to ask exactly where inside this is H and Y and which template we are using. So that is the second step. That is the localization loss.
So we draw bounding boxes, right? But 13 cross 13 don't give you sharp outbox. So we need to traverse over the 3 cross 3 kernels and then we need to figure out where the object is.
Repeat that.
So in final output, generally we get a sharp bounding box saying, okay, this is the object, exact object. So, but 13 cross,
Sharp
I
bonding
mean
box.
like exact bounding box of an object. So with 13 cross 13, we cannot do that
Why can't we do that?
because 13 cross 13 is its resolution is not sufficient to mention the
Yeah,
exact boundary.
no, it is sufficient to mention any bonding box. Let's say this is the particular cell, right? First of all, I can make my centroid anywhere. This can be my centroid, and I have this template. I have the H multiplier, so I can make a longer template. I have the width multiplier, so I can make a thinner template also. So same template can be modified into different bonding boxes. So I can literally take this and draw it here.
So when performing NMS, how do we decide threshold?
What do we decide?
Threshold. When performing non-maximum.
Threshold,
Yeah.
non-maximum threshold.
Yes.
Non-maximum threshold is again your what is it called? GRE coming in picture. Non-maximum suppression. Sounds fancy. What does it mean? Sorry?
It takes a threshold and
No, there's no threshold here. See how English is playing here? What is non? Not. Maximum is what? Max. Suppress is what? Don't take. What is the reverse of this? What does it actually mean? Take the max. So non-maximum separation is take the max. You just sort it and you just take the first one. Literally. Okay, this was your session 22 by the way. So let's come back to.
Not just classification. So x and y values are with respect to the original image or
With respect to the cell,
with respect to
we
the
have
cell?
13 cross 13 blocks. In the block, where is the x? Where is the y?
So why it is 13 cross 13? It can be any other
Anything,
dimension.
yeah.
It can
We're going to see YOLO was designed to beat someone. So when we cover the YOLO session, we are going to ask many questions. And when we cover the YOLO algorithm, you're going to ask many questions. And I'll look at you and you'll answer yourself. And your answer to most of the questions in YOLO session is going to be to beat SSD. To beat SSD. You're going to ask me why is it 13 cross 13? Then you look at me, I'm going to say, okay, to beat SSD. Then you're going to say why 5 templates? I'll look at you, then you look at me, okay, to beat SSD. So there are many things which we have done in YOLO, it is just to beat SSD. Whether something happened in the YOLO original CVPR when the YOLO V1 was being launched, there's something very humiliating happened for the YOLO team. So all they had left in their life was to beat the hell out of SSD. Okay. So you have to keep the resolution of the channel as high as 13 cross 13 cross 5 cross 125. Now this is one approach. We have another approach in SSD where we use something called region proposal. In region proposal, again the resolution of the output is going to be very high. This is not definitely as high as, let's say, your semantic segmentation where which literally have 400 cross number of classes. But this is literally very high, 13 cross 13 cross 5 cross 125 if we have 100 classes. So it's a very dense prediction layer at the end. You have to make sure your network is carrying multiple receptive fields till the end. If you're not carrying multiple receptive fields, then you will not be able to predict most of the objects. If your only high receptive fields are in the final prediction layer, then it's going to be very difficult for predicting small objects. You have to train the network on all sizes of the images. When we cover YOLO, you'll be surprised at how smartly they have actually trained the network. What is the resolution of the image they have trained the network on? That's not a constant. They keep on changing. Every 10 epochs, 50 epochs, they keep on changing the size of the image which it is being trained on. Very smart architecture. Okay, all of you have seen this network earlier, right? Now you were to rewrite the network for image net data. What all would you do? ImageNet has a variable size of the sample images. What will you do? Right, let's look at some of the options. You're going to remove the fully connected layers, right? Second step, you're going to add skip connections because we are talking about our object size being very small. If you want objects, small object sizes which need to be fed back, you have to do a skip connection here. Now in YOLO, the skip connection is from the 13th layer to the last few layers. Why is that? Why is the 13th layer? What they have done, they've taken the same architecture, and in this architecture they've gone to the 13th layer, and from 13th layer they've connected a skip connection to, let's say, last layer, not little last but lastest.
Texture, some pattern will be there.
So what was happening, some small objects were not being detected, so they added that skip connection to detect those small bonding boxes also. Now how would you know it's 13? You have to go on the 13th layer. You have to train the whole damn network, and then you have to figure out what is the bonding box you're not getting. Then you have to go to that receptive field and then connect. Clear?
What you're saying is for each, first I have to try for each channel and then I have to say whether it's 13 layers optimal or it's 12 layer or 15 layer.
No, you have to first check what is the size of the bonding box you're not getting. That will give you an idea. You have to go to 11, 12, 13 or 14 and then you test. Okay, assume you have this network to build. We have input layer 5, input layer 6, okay. Which API are you going to use? Functional API, right? And this is a very interesting problem right now, what you're seeing here. There's something, so right now we are using DENS and all, but what you need to see is that it is possible to feed 3 different input images or data to one single network. Give me an example of how you can use this. We are sending in.
Combine two images, like from data communication, same thing I think.
What basically we are saying, we have the input 1 and then we have this input 2, and we can feed it to one single network and make the network predict something. Right? What we can do, we can send in, let's say, a normal image, RGB, and I can also send a thermal image and then do some sort of medical analysis. I can send in the left image from the left camera, I can send in the right image from the right camera, and I can predict the 3D of the model you're looking at. I can send in one image in a telephoto lens and one image which is the depth, wider photograph, then I can actually know the depth of the image. I can also send left and right image of the robot and I can get the depth again, which is again 3D. I can send in MRI image 1, MRI image 2, and MRI has 13, I think 16 channels. I can send all the 16 channels sequentially, in fact parallel to my network, and then I can predict literally the 3D of the, let's say the tumor or something else you're looking at. Right? It is possible to send in many different inputs, and you're already doing that. How many inputs you're sending right now? 3. You are already sending 3. Right? But what we are doing right now is that you are sending this image directly to the network. Right? This is your R and G and B. You are already sending this right now. But what you can also do, you can send it. You can send R, which works on first this, which is worked on by this neural network, G, which is worked on by this neural network, and then B, which is worked on by this neural network, and then send that. Right? Now let's go from image domain to some other domain. This is your image coming in, you have RGB, this goes to a neural network and then this goes to another neural network. Now this is the machine vibration data which is coming in, that goes to some deep neural network and then we send it to this deep neural network. This is a sensor data, let's say you have a microwave sensor or micro radar sensor. That radar sensor goes to some other neural network and then that gets fed in here. So there are many different neural networks you can link right now, and this is possible in your functional API, right? And especially this one, what you're seeing right now is your autonomous car navigation data, where you send in the image which is coming from the camera, you also send in the data which is coming from the radar, and you combine both the images. Your imaging data is just 2D pixel of what exactly you're looking at, and your radar data is how deep or in what depth exactly you're looking at. So when you have both the data, then you can actually predict much better. So you can feed in both the data. All you have to figure out is this small deep neural network which can make sure that both the data can be stitched together. Right? You already have that done in your RGB image. RGB is a similar kind of data or a similar dimension data. Because similar dimension data I can mix properly, I can use my 3x3x1 kernel to look at both at the same time. All what you have to do, you have to convert this in, let's say, into, I'm picking just random number, okay? 17 cross 17 cross 10. After some convolutions, you have got this data converted into 17 cross 17 cross 10. I'll also have this converted into 17 cross 17 cross 12, 10, doesn't matter because I'm going to concatenate. Now I can concatenate, create a new 3 cross 3 kernel, it convolves on both at the same time. Any question on this?
How do we check the loss for different kinds of domains?
Oh, you still have to provide some jobs to Indians, right? So there's going to be Indian sitting somewhere who's going to be looking at his data. Oh, car. In the 3D data, he's going to have a 3D tool. He's going to say, oh, car. So some humans are still going to be sitting and working for machines.
But training data will be very less for this kind of thing.
Yeah, there's a company which is $1 billion company now. I'm just forgetting his name. It's just raised, I think, $200 million. And all they do is bonding boxes for.
So even AWS has a feature to label people. You have to submit the job and they will label you.
Turks.
Metaverse.
Alright, we are running slightly slow for the day.
Labeling is in fact a 1.2 billion business. It's not bulk, isn't it?
There's a company at 1 billion.
Labeling itself is a one.
Yeah, huge
Someone
business.
wants to do that.
Okay, you're working on extremely constrained hardware. You'll pick your options for your network which will help you save computation as well as RAM. Still amongst the one, which is the worst option. Fully connected layer is going to be the worst possible option if you are going to design your deep neural network. In any given scenario, not only on limited hardware. Your trained network will be finally deployed in a scenario where lighting conditions might vary. This means that your network will have low accuracy in the deployment. This is sort of overfitting. Do you agree with this?
Yes.
Right? The technical definition of overfitting is what? The gap between the test and the train, or test and the validation, right? So that is what is happening right now. Do you think dropout will be able to help you in such case? No. That is why dropout is going out of fashion. You're going to see more and more new networks are not using dropout. Dropout adds that black pixel essentially. It is not going to help train an image which looks dark. It is going to help you train an image where there's a hole inside, and that whole thing can be done much better by cutout. So dropout is going out of fashion.
In this cutout will not help much now because it's a dark image.
Cutout will not help. I did not say that. I said the punching hole is done better by.
Augmentation will work in this case.
Yes, image augmentation is what we have to
You
apply.
can change the brightness.
Yes, it is guaranteed that your model will finally be deployed in a very low lighting condition. However, the training data you have was collected in a very bright light condition. What all will you suggest? Okay, first thing we are going to do is the mu sigma image normalization or image standardization. Right, you have to normalize the data to make sure that the data itself is normalized. The data itself does not have a wide variance of the images coming in. Second, you are going to apply image augmentation to make sure your data is trained on dark images and bright images. Then you're going to use batch normalization. There's no avoidance with that. And last, you're going to also do min and max image normalization. But without batch normalization, you can't train the network. So that has to be there.
Why do we need both min-max and mu sigma?
Yeah, why do we need both min, max and image standardization?
Those are different kinds of normalization. We don't have to do both, right?
Sorry?
So one mu sigma should be just for normalization, subtracting by me and dividing the kind of variation. But min max is a different kind of normalization. So you can do either of them.
We need to do min max and then we need to bring them to a range and then we can do music.
What is min max?
Bringing them to a specific
Subtracting minimum divided by divide by
zero
the difference of minimum and maximum.
Divide by range.
maximum and minimum, dividing them into a range where entire data will be in a specific maximum.
Okay, so let's say I have this kind of data.
You want to bring the 10 to 0 and the 200 to 255. That's what min max will do.
I have to what?
So you push the 10 to 0
Correct?
and the 200 to 255. So that will be min max.
That will min max.
So you're doing a mean sigma, then you shift the mean. Why do I put the 0? You kind of shift the mean to 0, I guess.
Yeah, should be.
And then you can tighten that.
right? So what we are doing essentially is look at the problem right now. It is guaranteed your model will finally be deployed in a very low lighting condition. However, the training data you have collected is in a very bright lighting condition. What would you add to your network? Now, when your data is collected in a very bright lighting condition, what is the kind of data you have? When you're saying you have collected a data set in a bright lighting condition, this is the data you have, right? And all of this are 0, right? And when you are collecting the, I mean, when you are deploying the model, how your data looks like? This. So again, all this data is 0. So basically, the data you have for training does not exist for validation, and the data which is coming in validation was not there for your training. So what you have to do, you have to get some sort of symmetry where there's some sort of overlap in the data. So what we are going to do, first we are going to clip our data. This is the data, kind of data we have. We're going to clip it here and we're going to clip it here. And then we're going to fix the skewness. We're going to normalize that, minus normalize divided by standardization. And same thing we are going to do for our other data also, because we have added this in the algorithm. What is going to happen first time? It is going to be clipped here and then it's going to be normalized here. So we have some symmetry in the data coming in and the data we are training it on.
If we are normalizing on training data set, is it okay? Means is it necessary to normalize on test data set?
Yes, academically, if you find online, if you go online, what you're going to see, it is always, so we have test data, we have train data, and then we have validation data, right? This kind of data set we have. What you're going to find online is that we take our mu from our train data, we take a mu and sigma from our training data, and we apply this to our test data, we apply this to validation data. This is for academics only. This is not what happens in real time.
We shouldn't like apply this for test data, right?
We should not. Right now when you are collecting data set, or as a college or as a group, when you are creating a training data set, what you are doing, you are confirming as the company or as the organization that this and these are homogeneous data sets, which means you could randomly shuffle and pick. But that is not what happens in real life. In real life, this is not going to be similar, right? This is, for example, this is basically telling you that the guy who has written the book or the guy who has taught you has made the question paper. But that is not the case. That is never going to be the case. The guy who's teaching you is not going to be the guy who's going to be interviewing you for the job. So your test data set or your validation data set, they're going to look very different. So you have to gather a new mu and new sigma and then apply that. But in academics, if you follow online, if you see online, this is something which is said that you have to use the same mu and sigma, but that is not what we do in deployments. Is cool? Alright. Now we are working on a particular network, output of which looks like this. Right? So as a radiologist for image recognition, what do you see? Checkerboard issue, right? You're seeing a tumor here. Yes, no? You're seeing the image tumor here. You're expecting much smoother images in the images. What could be the reason? We are doing deconvolution. Deconvolution has checkerboard issue, right? What is one of the things we do in deconvolution? We are going to take our image and we are going to split our image, expand our image and fill it with zeros or maybe replicas of the pixels we have. We are doing convolution with strides. The moment we have strides, we are reading some pixels more, we are going to read some pixels less. We are manually upscaling some channels and then concatenating with some other channels. Right? This is something which people used to do. Now we have that space to depth and depth to space algorithm. But before, when you want to do concatenate, let's say 5 cross 5 with a 7 cross 7 or 5 cross 5 with let's say 9 cross 9, you're going to take 5 cross 5, fill it with zeros, make it 9 cross 9 and then add. Again, the same issue comes up. As long as you're taking a channel, expanding and adding something in between, you're going to be facing same issue.
But group convolution does exactly that.
Sorry?
Group convolution will do exactly that.
No, group convolution we had padding to add on the side.
Padding same, padding zero.
No. So the checkerboard happens when your image inside has the issue. For checkerboard to happen, you have to read one pixel more than the other. When you're using padding, you're adding your pixels on over the edge. So even if the issue is there, it is going to be over the edge. Your image is not going to look like this basically if you are using.
The center it may not look like.
Yes.
Should convolution be the highest right? Strides are always low. It should be the highest right convolution.
Yeah. Cool. Okay, now let's go to the 9th quiz. Okay, what is the relationship between the amount of training data available and the IOU? What is IOU? Sorry? IOU means you owe me something. Okay, so in IOU, what do we do? Essentially, this is again going for the bounding box kind of problem. Now, this is the bounding box I wanted, but the bounding box your network is giving us is something like that. How do we create a loss function out of this?
You see the overlapping area.
We see the overlapping area. So this is the overlapping area. So we say this is the overlapping area, and then we see what? The total area. So total area is area of the green plus the red. This is what? IOU. Okay. You owe me. Okay. This is clear? Yes, no? And you do it for 100 images, this becomes map, mean average precision. So you're going to see your bounding box networks or object detection networks, they don't have accuracy. You'll never hear YOLO has accuracy of 90%. You'll see YOLO has a map of 17% or 27%. That's the kind of number you're going to get. Okay, in a network, a layer has layer 9 has 100 kernels creating 100 channels. Just after this layer, we add dropout with the value of 0.2. What is the probability that layer 10 will receive the channel number 14? You've seen the answer.
It's obvious.
Okay.
There's no
There's
We
a
are not
relation.
dropping
relation.
the channel.
Is this clear? Is this clear? Right? Full channel is going to come in. There's no, we are not dropping a channel. This is not spatial dropout. This is dropout, which means in a channel I'm going to be dropping some pixels. If this was a spatial dropout, then the answer is going to be 20%. Sorry, 80%. Good. Any question on this?
Don't like concepts like IOU will be like covered in more detail because we haven't like covered those things.
Yeah. So that's a YOLO and other. So YOLO we have two. Then we have SST. Your basically region proposal network. So we have 3 sessions on that. Okay, your object detection database shows that the majority of the objects are under 45 cross 45 pixels. If the size of the image is 128 128, what is the maximum ratio of cutout section you would like to go ahead with this? Go ahead with.
So why is it not 0.14? 0.5 you will generally in that ratio you will miss out the entire image. Why is it 5?
If you had implemented the algorithm, then you will not ask that question. You're done your assignment. Then has anyone any question on this? Ask me a question only if you've done the assignment. If you're not done the assignment, you can't answer this question.
You're concerned by 0.5 because it will hide 50% of the image. So how it will hide?
Have you done the assignment? Then don't ask the question. Any questions now? Okay. Okay, first of all, this is the image and I'm going with 0.5 as a cut of this, right? Where should I draw it? Here?
Inside
No,
the
inside
image.
the image.
Yeah, so that's the point. It is not always inside.
Okay, it could be.
It could be here.
Okay.
But there is huge chance to pick up the main image.
Okay, let's see the chance. We're talking about chance, right? So this is 16,
Okay.
right? This is 8. Then I have this 8 also. So I essentially have what? 32 cross 32 image. What are you cropping? 8 cross 8. You're cropping 8 cross 8 out of 32 cross 32. You see what is a number here? This is 4, this is 4, 1 by 16. You have 1 by 16 chance of actually cropping the area you're concerned about.
So it's okay.
It's okay. Dropout, if you see the cutout paper itself, they go with 50%. Because this 50, 16, this 8 cross 8 is actually just 25% of the image. Right? If you're saying 0.5, you're saying half the size X and half the size of Y. Is this part clear? So you can actually go with any of these. You can go with 0.35, you can go with 0.5, you can go with 0.15. But you see the score is 0. Why the score is 0? EVA 1 did not agree with me on this. They said no, we do not agree that I can go ahead with 0.5. So we said okay, go ahead and implement in the your code Once you implement 0.5 in the code, then confirm 0.5 can be used, then we are going to change it. They have not yet confirmed this. Right, so when you are doing your assignment, use a cutout of 0.5, see for yourself, it's not going to change anything. In fact, go and look at the paper. If you look at the paper, they are using 0.5.
So, question related. So, if you have a 45 to 45, you, okay, so the ratio is in area or not in dimension, right?
Sorry, repeat that.
Maximum ratio is in terms of area and
This,
not in dimension.
this is not area, this is dimension. That is what people forget. When you say cutout 0.5, you're not saying 50% of the image. You're saying your x is 0.5.
X is 0.5. So
Which
in that
means
case, you are almost going toward half of the image, like
1/4 of the image.
50% of 128.
1/4 of the image.
That is fine. Agreed. So my question is,
One
the
fourth of
area you are cutting the
one
size.
fourth one fourth of the image you are seeing 128 128. But that's what we are going to see in the algorithm itself. That my image is not 128 to 128. My image is, if you use a cutout of 50%, your cutout section is 64, which means my image is now 256 cross 256. So you're cutting out a region of 64 64 in 256 256, which happens to be 116.
How did the image become 256?
I mean, it's an analysis.
Because of this. When you implement the cutout algorithm, you're going to see that we cut out this also, which means the cutout section is actually here. So we allow the cutout centroid, let's say this particular initial point, to be here. So if you have this image and you're seeing cutout of 0.5, essentially this quarter can be flipped over, and this is the beginning of the cutout section here. So we actually, this is the area in which my cutout can work. It's very, very code specific. That's why if you have done the code, then you're going to, and the reason is that we always don't want to cut something. We want some sort of probability to always play around. So now if you do something like that, I'll be able to cut off this region. I'll be able to cut off this region. I'll be able to cut off this region. If you force it to be always in the image, then you're always going to be cutting out something important. So make it, in fact, give it a much bigger area and then cut out regions so I can cut out. So sometimes it's a waste also, which is what I'm talking about. But being probability, you're going to see that the wastage is going to be equal. Like this box is going to be equal number of times probable as the one which is going to be exactly on top of your object. Because it's random.
We are cutting out part of the image, not the object. The center is the object, right? This is the whole image.
We don't know. Maybe my object is here, and you're cutting out this part.
Right.
That is also possible. And let's say my object is this big huge thing, right? And if you are implementing, if the size of the object is equal to size of the image, and you're implementing a cutout, you're always cropping out some part of the image. That is a bad thing. So what these guys smartly did, they actually said my region can be anything. I will like to have, okay, this is my plane. If it looks like, yeah, it looks like a plane, fine, okay. I want to cut out just the tail section, right? I will want to cut out like that.
So in every batch we cut out different parts, or?
Yeah, every time you have a different cutout. That's what, you have not implemented the code yet. It's a very, very important algorithm. You can find the code online also. You just have to copy and paste. But copy paste is also now heavy key, right? Copy and.
But cutout has to be, need not be exactly in the image. Your cutout can be, I can just have some part. This is the whole image.
This is the image.
Right. So, but the cutout is going outside the image.
Because if you have implemented the code, you will see that you allow your cutout section to go out. Because we will like to just chop off the early part of the image. We'll just like to chop off this part of the image. And this indirectly says that if you implement like this, that sometimes cutout happens, sometimes cutout don't happen. So you don't even have to give any probability for cutout. When should it happen? So every step is going to cut out a very small portion of the image or a big portion also.
One side question, if I may. Go ahead.
Yeah, but with this, size of image is not increasing. It's still 128 to 128. It's not becoming 50 places. This is fine.
No, the playing region of cutout has increased here. Size of the image has not changed. The playing region of the cutout has increased here. Like where all it can be. Where all it can be.
Okay. Okay, in that sense, yes.
So one thing side question related to the assignment more than the quiz is the tail of the cutout.
The tail of the cutout.
What you feed the cutout with is supposed to be mean of all the images, right?
Yes.
So which fundamentally means, and I remember in the paper it mentioned it's better to do an image normalization and then fill it with 0 so that you don't have to compute mean in the first place, or kind of it's taken care of.
Yes.
Is that the recommendation, that you do
No.
Okay.
If you see implementation of the original authors, they did a cutout and fill it with the mean, not a black.
Do you ever talk about normalization?
I looked at the code, and any other, in fact, you're going to see any implementation of the cutout, they are going to be filling it with the mean.
The mean of the entire data set or
Entire data set.
And in the paper, the pictures that were coming with the cutout, the patch was always on the image.
No.
But some of the images did not have a patch because only.
And some of the images had a patch like this also, like that. This one. Okay, I'll have to move. In network 1, N1, we use sample pairing as our image augmentation strategy for 100 epochs. We train same network for 100 epochs, but this time without sample pairing. Network, okay, is this clear? Do I need to go into this? Right, we have bad accuracy for training and good accuracy for validation. Okay, a class activation map shows most of the activation for the classes are concentrated towards a small area in the image. Select which all are true. Our network has a heavy potential for overfitting. What is class activation map?
kind of
Highlight the part where the same.
GradCamp.
GradCamp, the one implemented, if you have implemented.
Yeah, it might be seeing only some part which is present in training data network.
Yeah, so whenever you're seeing any class activation map, that heat map of where my object is only concentrated in a small area, which means you're only focusing on a small area of the object also. There's a whole bird, but you're just looking at the bird face and you're saying this is a bird. So you're seeing overfitting. Moment that bird picks a flower, you're going to say it's not a bird because the area where you were to focus is not there anymore. Cutout should fix this problem. Right, that is what we saw earlier also. Recap should fix this problem. Recap is a fancy cutout. Dropout should fix this problem. Not at all. Why is that? Why dropout cannot fix this problem?
We are not exactly removing the part. Spatial dropout would.
Yeah, spatial dropout will, but cutout will not. See, let's see what happens. This is one of the channel in which you have done implemented cutout, which means this pixel is black, which means whatever this pixel was looking at is not going to be transferred. Yes, no, no. Why no? Because whatever this pixel is seeing, this pixel also seeing. Let's say the receptive field of this guy is 13 cross 13. What is the receptive field of this guy? 13 cross 13. You're dropping this pixel, you're not dropping this pixel. So when you're dropping this pixel, 13 cross 13 area is dropped. But if you're not dropping this pixel, that 13 cross 13 area, at least your 12 cross 13 area is still there. So maybe intensity has dropped down, but you have not dropped the particular feature. That's why cutout is not going to be really helpful. Or dropout is not going to be helping here. Elastic distortion should help this problem. When you do elastic distortions, the area where it is focusing, sometimes it's not going to be there. Sometimes that area itself is going to be so squished that it has to look at some other area of the image also. So whichever is going to manipulate your image spatial data is going to be helping this particular problem. L1 and L2 regularization should solve this problem, not at all related to what it does. Okay, a network is run for 100 epochs and it roughly takes around 10 hours to finish. We are implementing 2 randomly selected image augmentation strategies picked from the 5 options. Okay, if we were to run a reinforcement learning to figure out the best training strategy, how long will it take to train this algorithm?
10 into 10 plus 100. But extra data, it will take 100 hours. And then main training data, it will take 100 hours.
Is this clear then? Quiz question?
I didn't hear what he said.
Can you explain again?
So there will be extra data we are adding for everyone. So for all those if we calculate it will take 100 hours. And for training data itself will take 100 hours. We are adding extra data, right? 20% while doing reinforcement learning.
20%.
No, 20%. Ending it only.
so if the scheme
EVA
of
was
things,
scaling.
so
So
it came up
basically,
with this
Scale
UA
by 20%.
intuition.
is it not like that we have a 5 different
So it's 5C2, right?
Yeah.
algorithm we need to
So we have 5 options,
right?
right? And we do 5C2 because we're picking 2 randomly. This gives us 10, right? Yes, no?
No 20. Not for the order.
5 into 4 divided by 2 into 1. This gives us 10, right? But this ordering matters a lot, so we have to multiply by 2 because doing a rotation and cut and doing cut and rotation are different things.
Tiny source.
right? So this becomes actually 5c4 if you think about that. Not 5c4, but 5c2. Yeah, 5c2 and yeah, 5p2. Yeah. So I'm not really remembering those permutation combinations. I don't want to say that. But what I see here is 5c2 into 2 because there are two options for each. So you have essentially 20 options here. Unfortunately, because the number of options are too little and you have only two steps, you cannot say which the first step is bad, so don't take the second step. You do not have that option. For reinforcement learning algorithm to work, you literally have to have a chain like this. Take action A, then take action B, then take action C, then take action D, then take action E. Right now we have to take action A and then take action B. Because of which we don't know, reinforcement learning is really a bad algorithm to implement here. Right? What we are saying is that if I take A and if I do B and if I do C, this is really bad. So I'll never be taking these steps. What are we doing now? We are taking a step A. I don't know if it's bad or not. You met someone for the first time. You don't know it's bad or not. You will know only after years. Right? This is the first meeting. This is the second meeting. You have to meet people at least twice to know how good they are or bad they are. Sometimes, like most of the times, like I'm talking about like good people. They're bad. You can figure it out, right? So for any action, for any reinforcement learning to work, we have to have depth in the problem to be able to solve it. So this is not going to be working. So essentially, we have 20. We have to run this algorithm 20 times. Each run takes 10 times, 10 hours. So 10 into 20 is 200. That's the answer. Is it clear? Right? Only if we said that we have like 20 options. In this 20 option, we can pick any number of options. Let's say we can take 10 options. Then this is a reinforcement learning problem. Should I rotate first? Should I crop later on? Then we'll learn that doing a rotation first and doing a cutout later on is a bad thing, or doing a cutout and then doing a rotation is a bad thing.
Won't that be random in?
Sorry?
Won't that be random in a like some like when you are training it will might scale first, rotate second, and rotate third.
All of that is random in normal algorithm. In reinforcement learning, it has to go through every single step to see it's working or not.
So you're saying that in one network what we train it will always scale first and then rotate,
Yes.
and in the other network it will always rotate
And
first
then
and then.
scale.
But what if I mean choosing the randomness is a better option? Like first in the same network, sometimes scale first, rotate next, and sometimes rotate.
Then you have to design the algorithm like that, which allows it to pick strategy like that. But the strategy we are picking is like we are picking strategy sequentially.
Okay, but it's not.
Sorry?
It's not mentioned.
It's mentioned here. We are implementing two random. That's the first line. We are implementing two randomly selected image augmented strategies sequentially picked from the. Okay. You're trying to train a You're trying. Okay. You're trying to train a car detection network. The training data with you has good images of car without any obstructions, but you are deploying the model where the pedestrians are going to be walking in front of the car. Which data augmentation strategy could you pick? Right? Why not recap?
Car patches is all nothing.
Car patches is one. We need 4 classes for recap to work. Why not sample pairing? Sample pairing is car on top of a car. I need to not see a portion of the car. GAN based approach for creating new car images. It will not automatically generate a human in front of the car. A GAN trained on car is going to show a car. Okay. You're trying to train a network for automatic number plate detection. Please remember, this is not detection. This is detection, not only recognition. So we are doing both. We are doing character recognition and okay. Which image augmented strategy would you not pick?
Six will become.
You will not definitely flip the image and then read it.
So why not cutout is an option?
Sorry?
Why not cutout?
Why not cutout? Like why would I use cutout?
Yes.
Yeah, cutout. So cutout is new really. There's no you will never be able to think about a problem where cutout is not implementing.
So you're saying this is a problem where we have to recognize the digits as well.
Yes.
But if we put a cutout, we are not able to
No,
recognize.
you have to then change your bounding box also. This is not my car number, okay? Now this is the image you have, and what you have done, you have taken a cutout. Let's say this is the cutout you have, right? Now you're going to be feeding this as the label for the image to predict. Your new label is going to be 03MT9539. And this is much better because now you have far better data as compared to just looking at K03 and so on and so on. Because if you train your data always on K03, what is network going to learn? That you have a K. And networks are really good at that. It's going to see it looks like a K and it's going to patch in K. And you're never going to punish that. Why? Because all your images had K.
Okay, we should also cut out the labels.
You have to cut out labels.
I was thinking cut out means we just cut out the image.
Don't be lazy, man.
But if we have a multi-state data and all, in that case, it will.
It is always better to cut out because if it is not there, you need to say it is not there. See, when you're making this number plate detection network, right? What is the final use case? You need to see the number which is there.
Right.
If you do not cut out, what is going to happen? It's going to hallucinate and patch in some data. Network is going to hallucinate and patch in some data, right? It sees a number there if it is not there. So you have to force it to not see a number if it's not there. And if you're a traffic man or traffic policeman, you have to make sure that that number is not there. You have to punish the guy. A broken number plate is punishable offense.
The label, I mean, if there is no data at all, then I need to go to every image and then see, okay, this label is, this K is not there, and I need to modify the label.
No, it's algorithmic, right? You know the location of the label, you know the cutout, you just patch it out.
Yeah, no, but since you're saying K is 03, removing K, so it will never learn K, right? Now, if I'm doing Karnataka, I keep removing K, it will never learn that K is a number, right? If I use cutout, no, I'll be removing K every time, or sometimes. So how is it a good strategy? Instead of getting the
Because
first
there's
side.
03 also, there's MT also, there's 9529 also, there's some other digits also. You're going to crop a particular region of the network out. And moreover, it is actually helping you make sure that Indian number plates are like what? The worst possible number plates in the world, right? This is missing. Or maybe this is missing. That is what number plates are. Or sometimes there's an occlusion. There's a traffic, there's a bike's bottom mud guard, the back mud guard is hiding a part of the number plate. You still want a network to predict in those cases. So you're actually adding occlusions here.
And you're not going to cut out K each time, right?
It's random.
Yeah, it's
And again, if you calculate the randomness, you're taking an image, inside an image there's a number plate. See what is your concern right now? This is an image. In this image there's a car. That's the number plate. Right? And then you're concerned about cutout. And if the number plate is big, if the number plate is still big, remember cutout starts from here. You're concerned about cutting out part of the image or maybe the whole. If you cut out the whole thing, it's good. Now the network is forced to say it's not, there's nothing there. You can't,
Remove the label too.
the whole label is gone. Okay, act like a deep neural network, okay? I'm asking you, what is this? Read the number plate.
03MT.
No, you are a deep neural network.
Okay, K and 03MT.
But what is this was MH?
That's okay, sir. I understand that thing, but we need to go to labels and we need to remove everything. That will be like manual work, right?
No, it's an algorithm, right? You have the image. In the image, you know the location of the label. Some human has already done that. And you know this is K, this is A, this is so on and so on. You know exact label. Otherwise, you can't train it
With location.
with location.
And what is label attentive?
Sorry?
Label attentive cutout?
Label, that's what we're doing. That you're cutting the label out also. But the cutout normal is you're not cutting the label out. You're forcing it to still predict something. The better one is going to be label attentive cutout. Okay, what would be the fastest way to increase a data set with less number of classes?
Why not cutout?
Think.
Cutout is easy. Generate some random number and remove it.
Cutout is the same image manipulated.
And sample clearance, you have to take image and new images.
So we should not do cutout if there is less amount of data.
That's not the question. The question.
that's true.
I got it wrong, so I assumed
No.
But it is recommendable to do cutout on medical images.
Yes. Label attentive cutout. Whenever you're using medical or other field and you're talking about bounding boxes and regions, you need additive cutout. In fact, medical data is used a lot because medical data has very fine tubes and capillary where you have to focus there. So if you train a network which is on medical data, it's just going to look at the initial part of the data and not look at the rest of the data. So we use cutout literally everywhere. That's what it's a ReLU. You will not be able to get rid of cutout. Every algorithm you're going to see will be using cutout. That's why you need to get really well versed in cutout. Cutout is there in NLP as well. Cutout is so powerful that we have added back to NLP.
Why we are not doing here also with sample pairing?
Sorry?
Along with sample pairing, we also can use cutout.
The question is different, right? The question is that what is the fastest way to increase the data set? The question is not which augmentation strategy should we use. The question is what will be the fastest way to increase a data set with less number of class images. Now when you're doing sample pairing, you can take one image at a 0.1 transparency, let's say, opacity, other is 0.9, and these numbers are infinite, right? 0.11, 0.89, or 0.1, 0.1, you can literally create as many images as possible.
Facial and all those things like data augmentation techniques, that will be part of it.
Sorry, that will be?
For sample pairing, we can rotate and do
Poor man's.
Literally becomes infinite. Sorry?
Poor man's.
Poor man's data augmentation basically. Right? So that's what we can do. But others are not available options here basically. You'll not be, if you are going for GAN based approach, you're waiting for a month to train a network and then implement that. Then in Bayesian network again, you're going to wait for 15 days because faster than reinforcement learning and then implement that. It's not fast. We are saying what is the fastest way. Okay. Now, what are the benefits of training a network at 200 cross 200 image as well, even though finally it will be deployed at 400 cross 400? This is something which YOLO does, and this is something which is very, very interesting and something you'll appreciate when we actually cover the YOLO algorithms. Now, look at the first thing, network trains faster. Right? Before looking at that, these options are randomized. Maybe not sure about this quiz. Okay. Now, this is an image. Inside the image, my object is this big. Yes, no? If I scale my image becomes this big, and my object becomes this big. Right? Which means if I scale my image, if I train my image on 200 cross 200, I'll be training my network on this kind of object sizes. Yes? And if I'm training my network on this kind of images, it is going to be running 4 times faster than this network. My batch size literally can be 4 times. Is that correct? Right? Instead of 400 cross 400, I'm using 200 cross 200, which means I'm only using a quarter of the RAM. I'm only using quarter of the area of the image, which means I can fill it with more batches, so I can actually get more training out of it, right? And because you have to do less number of max, which is for multiplicative additive. If this is your channel, my 3 cross 3 has to travel this and then this and this side and then so on, right? And it will be reaching here and then ending the convolutions. But if my channel size is half, it's done here, which means overall number of multiplicative additives which are required for convolution is less. The convolution steps itself are less, which means our network is also going to be running faster. So not only it is faster, I can fit a much bigger batch size, and we are getting small size images also to look at. So my network trains faster, large batch size can be used, and network becomes better at predicting smaller and medium size images because the whole data is becoming small. So now I can train my objects on my network on small size objects also.
Even at prediction, we reduce the resolution.
Yeah.
Arun, what are the disadvantages? Like network won't be deeper and accuracy will be less, maybe.
Why is that?
Because if we have an image which we are giving as an input 400 by 400,
Can,
and object
can you
size is
no? Can you please read this
okay, as well. Right.
as well? Okay. Let's start the session now. We are running damn slow today. Okay. Interpretability. Now, interpretability, we are going to talk about the kernel and the channel visualizations here. Okay. You need a break? 5 minutes? Okay.
Can you reschedule that? Yes, I attended that. That very lesson.
After you can answer, you can attempt the question.
Oh, is it? No, no.
You can attempt it again, just drop a mail to them.
When in a cutout algorithm, they are changing the shape of the patch, right?
No, that is random erasing.
Oh, that is the code which it pointed to in your assignment.
It has in random erasing they are using cutout many small cutouts overlapping itself.
Yeah, so the cutout that you were saying, where it is getting shifted out of the image and all that, where is that? That code we have to write?
That code you have to write.
Roman, this is online batch as well. I mean, is it? It's not live. This batch.
No,
You don't have any live batches.
no.
So how people remotely attend?
So as soon as the class ends, I upload a video in there.
So they watch it.
I've tried online many times. There's no viewer. 6:30 a.m. No one wakes up at home.
No. Okay. So actually, I have to shift to another city for my job. So just thinking how will I? So I will have to watch.
We'll talk in the class.
See?
We'll talk about the class.
For example, cutout, how do we decide? Let's say image size is 64 plus 64. You say like cutout, we can go big outside the image size also. So how do we decide what would be the boundary? Cutout till what boundary I can go? For example, let's say image size is 64 plus 64. So let's say cutout I can do it on the corner also, right? So how do we decide like image size is 64 plus 64 till which level, with what level go beyond that?
Yeah, so let's say cutout section 50%, which means 32 plus 32.
Okay.
So minus 32
Oh, okay.
to 64 plus 32. That's the range in X and Y.
So then in this last question, you said that we can train a network using like 64 per 64 out of the 32. Let's say I have an image of 64 plus 64. How do we draw 32 plus 32? Is that something zoom out do we need to do? Or
Repeat that. How
let's
do I
say
train on small images?
Yeah.
You have to manually scale the images and train.
Oh.
So, for someone who's looking forward to do like high studies in this field, what would you suggest? Like,
Start writing blogs on your LinkedIn and start making sure that you can write papers.
okay, and do you suggest do it in India or like go to like some?
Never in India. Always outside.
Sir, any research suggestions?
And what would
Because
the,
to write research,
You have to do your assignments, man. If you don't do your assignments,
So only one assignment. This is the first week I did.
so one more thing, like the code, I mean the curriculum or whatever we're learning here in this class, how is that? Is that like going to be the same level that we'll be doing in MS or PhD or?
this is the first 3 years of PhD.
Nice.
This is the first 3 years of your PhD.
Okay, and which do you know any famous universities that were that's good for this? Like
The scan by top 10 or top 20. Those are the ones you want to go in US. Then there's India. There's a TMU in Germany. Then there's University of Toronto.
So is there any research topics you could suggest so that we can work on some guys?
I can only so we are going to start with some around session 12 for you guys, the research group. Because what must happen is that you are going to form a group, and for that once the group is there, then we can proceed with the research part. So I need to start a project in which you're forced to make a group.
So one more thing,
will be
publishing
papers in that with. By the way, guys, if you are able to write your papers, you're going to be publishing it with
with you. It's School of
Carnegie Mellon.
Oh.
That's the fourth best AI college in the world.
Yeah.
what's the first? But how do we publish it?
What was the university name in Germany?
TMU.
TMU.
Full form? Munich.
How would Carnegie Mellon?
How would Carnegie Mellon?
How with? You said we would be publishing it with them, right?
So if you publish paper yourself, it's going to read your name and it's going to think who she and it's going to say cancer.
Exactly.
So you need to have someone from the research community who's there.
Yeah.
And my type is with CMU.
So
Unfortunately, you'll be the second author. Because his name is going to be first author. Unless the paper is really solid. If the paper is solid, you become the first author and his name is going to be second author. So first it's going to be reviewed by CMU and then it's going to be published.
how are the groups designed? So
You pick the group.
or if no one has someone does not have the group, then you have to narrate.
No, you have to form the group. Alright, let's start. Okay, now interpretability. Now we are talking about kernel and channel visualization. So it's slightly different from you find online. So when you find online, you're not looking at the kernels. Let's see that. Now we need to know what a model is doing, right? If it is weak, we like to make it better. If it is good already, then we have confidence and we can use it. And if it is better than humans, then we can actually get insights from this model. In fact, recently Google, day before or sometimes ago, I saw some video floating on WhatsApp where this Sundar Pichai. He was showing how the deep neural network models for something on the eye was able to tell more than what these. So we can actually do that. These deep neural networks can give us much better insights about our data set. We can't sit through this millions of images of or medical data coming in and perform on that. Now, how do we know that what our model is doing? How do we learn what our model is actually trying to do? So the first thing which came out on this particular field is called saliency. Now, just read that. The purpose of saliency map is to represent the conspicuity or the saliency at every location in the visual field by a scalar quantity to guide the selection of attended location based on the spatial distribution of the saliency. A combination of the feature map provides bottom-up input to the saliency map, model as a dynamic neural network. Very, very clear? Or there's GRE coming in front of you? Right? What we're saying is the purpose of saliency map or the purpose of importance map. Saliency actually means importance. So if you remove all the additional detail about that, the purpose of the importance map is to represent the importance at every location in the image by a color to guide the selection. Basically, to basically guide the user or guide the person who's viewing on the importance of that particular pixel. So saliency map is essentially a color or the scalar quantity. We are talking about the scalar quantity here, which is a color. We are talking about taking one particular image. In that particular image, we are talking about one particular pixel. We are talking about coloring that one particular pixel to a particular amplitude to guide the user to tell him that this pixel is this important. So essentially what you're seeing here is the pixels which you're seeing in the image at the bottom, that is how important that pixel is for that particular class. This is a saliency map.
It looks like thermal image.
It looks like?
Thermal image.
Looks like thermal image here because you're using the thermal image channels here. If you use the same channels you're using GradCam, it will look like GradCam. GradCam is exactly this.
What is the difference?
Sorry?
GradCam.
We are going to see now. Now, saliency, there are many ways of calculating saliency. This is one of the first ways in which we try to figure out how can we actually know what image or what part of the image is important. And this was one of the bad algorithms. What we are doing here is, okay, it's a very, now you will think that because you know about GradCam and if you have heard about it or read about it, then you're going to, okay. Now, this is your image. What you're going to do, you're going to go back and change this particular pixel. If you change this particular pixel, let's say when this pixel was not changed, you were predicting grasshopper with a value of 0.932, some that. Now I have to write a bigger value, 93236392329, something big. This kind of number was being predicted. But when you change that pixel, the value which is now predicted is what? Some change is there in the value. That pixel is not there, so your class accuracy is going to drop a little. Then you're going to do what? Change this pixel. You're going to see the difference. So if the pixel happens to be on top of your grasshopper, you're going to see that those values are going to have a much bigger effect as compared to the values which are not on top of the image. And that is what this image you're seeing here. Right? What you're seeing here, the white thing is essentially, if you remove that white pixel, that is the kind of effect we have on the prediction of that particular class. So you see, I have to run my network these many times. I have to change my pixel, check, change my pixel, check, change my pixel and check, change my pixel and check. So very, very slow. So this method came and went, and then we had to figure out a newer way. You can imagine if you're talking about network like VGG or AlexNet or GoogleNet, you're going to be, even if your inferencing is very fast, let's say you're taking 100 milliseconds, your image size is 400 cross 400. 100 milliseconds into 400 cross 400 is a lot many seconds than we like to wait for. This part clear? Yes, no? Yes. Okay. There's one way of calculating saliency, which got out. Now this is another way, which is called guided or rectified saliency, and we are going to see that through the GradCam algorithm. So essentially, first we need to cover the GradCam. So before we cover the grad camp, I'd like you to look at this particular video. Now, this video is something which is, unfortunately, the tool they've made is for cafe, so we can't use it directly, right? But just look at this tool and what all it can do.
Recent advances in neural networks have enabled computers to better see and understand the world. They can recognize school buses and zebras and can tell the difference between Maltese terriers and Yorkshire terriers. We now know what it takes to train these neural networks well, but we don't know so much about how they're actually computing their final answers. We developed this interactive deep visualization toolbox to shine light into these black boxes, showing what happens inside of neural nets. In the top left corner, we show the input to the network, which can be a still image or a video from a webcam. These black squares in the middle show the activations on a single layer of the network, in this case the popular deep neural network called AlexNet running in Caffe. By interacting with the network, we can see what some of the neurons are doing. For example, on this first layer, a unit in the center responds strongly to light to dark edges. Its neighbor, one neuron over, responds to edges in the opposite direction, dark to light. Using optimization, we can synthetically produce images that light up each neuron on this layer to see what each neuron is looking for. We can scroll through every layer in the network to see what it does, including convolution, pooling, and normalization layers. We can switch back and forth between showing the actual activations and showing images synthesized to produce high activation. By the time we get to the fifth convolutional layer, the features being computed represent abstract concepts. For example, this neuron seems to respond to faces. We can further investigate this neuron by showing a few different types of information. First, we can artificially create optimized images using new regularization techniques that are described in our paper. These synthetic images show that this neuron fires in response to a face and shoulders. We can also plot the images from the training set that activate this neuron the most, as well as pixels from those images most responsible for the high activations, computed via the deconvolution technique. This feature responds to multiple faces in different locations, and by looking at the decon, we can see that it would respond more strongly if we had even darker eyes and rosier lips. We can also confirm that it cares about the head and shoulders, but ignores the arms and torso. We can even see that it fires to some extent for cat faces.
Did you hear what he said? If you use decon, did you get that line?
This feature responds to multiple faces in different activate this neuron the most, as well as pixels from those images most responsible for the high activations, computed via the deconvolution technique.
Computed using deconvolution techniques. So what have we done here? We got that map, right? And then you do a deconvolution, which is reverse. You go back. So you get this map, and then you use the same kernels, figure out which image is going to give you this image. Is that clear? The reverse of the convolution process. In convolution, we go from layer 1, layer 2, layer 3. Let's say I'm at layer 3, I have an output. I need to know what input could have given this output. So I can do deconvolution there. If I do deconvolution, I can figure out this is the image which might have given this kind of channel. And you know deconvolution is not really great, right? We are going to fill it with some pixels. And that is what the result looks like.
This feature responds to multiple faces in different locations. And by looking at the decon,
you see that you're not able to reconstruct everything back. So deconvolution is a great thing, but it's not really great. Right? You will not be able to create everything back. That is why we have to come out with new techniques. We are going to check some of those.
One image is easy to see what different feature maps are giving. But when we train on a batch or whole data set. Then how we know that which feature map is having.
You have to manually go and check. It's manually going and checking.
You can visualize the one image and we can check it. But if I want
that channel will not show anything if that feature is not there. The channel is going to be black.
But when we train the whole set of images.
Yes.
So I'm not seeing for one image. What is the visualization of whole images of the last feature map or any image?
Every image you're sending in will have different feature maps. So you will have to look at that image, go in that channel and then check. We don't have, when we train with batch, we don't have one network looking at all the images at the same time. Let's say batch size is 32. What does it mean? You're running 32 parallel networks. There's not one network looking at 32 images. That is why we have to average the loss. My batch size is 32, which means 32 networks are parallel running. Each network is going to look at the image separately. Each network is going to tell me whether this was a cat or not, whether this was a dog or not. Finally, I'm going to take an average and train the whole network back. So if you want to look at the channel, you have to go for that network and inside that network and check that particular channel.
We can see that it would respond more strongly if we had even darker eyes and rosier lips. We can also confirm that it cares about the head and shoulders, but ignores the arms and torso. We can even see that it fires to some extent for cat faces. Using backprop or decon, we can see that this unit depends most strongly on a couple units in the previous layer con 4, and on about a dozen or so in con 3. Now let's look at another neuron on display. So what's this unit doing? From the top 9 images, we might conclude that it fires for different types of clothing. But examining the synthetic images shows that it may be detecting not clothing per se, but wrinkles. In the live plot, we can see that it's activated by my shirt, and smoothing out half of my shirt causes that half of the activations to decrease. Finally, here's another interesting note. This one has learned to look for printed text in a variety of sizes, colors, and fonts. This is pretty cool, because we never asked the network to look for wrinkles or text or faces. The only labels we provided were on the very last layer, so the only reason the network learned features like text and faces in the middle was to support final decisions at that last layer. For example, the text detector may provide good evidence that a rectangle is in fact a book seen on edge, and detecting many books next to each other might be a good way of detecting a bookcase, which was one of the categories we trained the net to recognize. In this video, we've shown some of the features of the DeepViz toolbox and a few of the things we've learned by using it. You can download the toolbox at this URL and explore for yourself. If you'd like to share what you find,
he just lied. You cannot download this and you cannot use it. This is on Cafe. It's very old. Okay. Sorry? And see it for yourselves. Okay. Now, so the problem is that this is in Cafe, but you saw some of the interesting things it said, right? You're training your network on ImageNet. ImageNet had cats and dogs and bookshelf and other things. What you are able to do is what? Extract eye, extract lips, extract text from the books, and so many different things which are embedded in the object itself. So deep neural network, a very simple deep neural network which you're training for these classes, it has to figure out many more classes internally to be able to predict these objects. Which means that we are actually not fully utilizing our network. When you're training a network for 100 classes, you're actually training a network for far more number of classes. And that is a really good way of looking at a network, because now if you can figure out a particular channel is working on text, then you can literally use this for text detection also. And you see the location of the feature maps, they are in sync with the location of those features in the image, which means you actually have a very loose bounding box already ready. That is why we need to know what is happening inside a deep neural network. Now another approach is activation maximization. This is what you are doing in a GradCam also. Now first of all, global average pooling. We have already started discussing about global average pooling, and I'll recommend that whenever you write a network, please use global average pooling. What are the benefits? It is more native to the convolution structure. Right? When you're using global average pooling, you're not going outside the concepts of convolutions and then implementing something. Like fully connected is not a convolution concept. Fully connected, you're taking 2D data, converting that into 1D, and then performing some other stuff, right? It's not in the bounds of convolution. So if you do something like global average pooling, you still be in the bounds of a kernel being there, and the size of the kernel here happens to be the size of the image itself.
If we use a gap, won't be smoothen the image?
No, a gap means converting the 1 pixel.
Oh.
It is not average pooling. This is global average pooling, which means you have a 13x13 image. When you apply gap, you get 1x1. This is not average pooling. If you are using average pooling on 13x13, you're going to get 6x6. Okay. No parameter to optimize. When you use
so even in GradCam, for example, we had name, and whatever image. And there are a couple of ways to get to 1 by 1. You can either put a convolution layer of the same size and get 1 by 1, or you can use global average pooling. So these are two different ways to
two different ways, but the benefit of using global average pooling is there is no parameter. Faster. There's literally no parameter. 13x13, you apply cap, no parameter. If you were to convert this into using flatten and then add a fully connected layer, you will be adding more parameters there. Okay, a layer with gap, a layer without gap with fully connected layer, which will have a higher accuracy. Fully connected, because we are comparing two wrong networks. You have added extra parameters there which will have some of the responsibility of predicting or some capacity we have added, right? And when you add a gap, we are removing that capacity. So this is not how you're going to compare. If you apply gap, what you're going to do, let's say you have a final channel is 7 cross 7 cross 1024 and number of classes is 10 or let's say 100. You apply gap, what do we have now? 1 cross 1 cross 1024. Now apply a fully connected layer. Never apply a fully connected layer on a 2D data. Is that clear? Now I'll have 1024 cross 100 to predict 100 classes. That same capacity we have added now in this particular manner. You're going to see it has much better accuracy. Any new modern network you're going to see this, that network ends at a 13 cross 13 or 7 cross 7, and we add a gap layer. It converts into that 1 cross 1 cross 1024 or how many channels we have, then add a fully connected layer, convert it to the number of classes we have. Much better approach for a network architecture. Okay, gap sums of the spatial information, which means it is robust to the spatial translation of the input. Yeah, we are summing the whole 13 cross 13 channel into one pixel, which means my object literally can be anywhere in the image, and I still get the average of that particular. Right, so it can literally in the whole image, in the whole channel, my object literally can be the gradient can be coming from anywhere, and gap has no parameters, so nothing to optimize. Is it clear? Okay. Now class activation map, let's look at grad cam. Before grad cam we had cam, but grad cam is the algorithm we need to know. Okay, now let's look at some demos first. This is a demo you can do, we can do at home. We are running short on time, so I'll let this guy talk about grad cam. There's no audio in the video. If you're sleepy. this is what it can do. Let's see how it does that. Now, the algorithm is very simple, and we're going to look at some of the steps. That it was highly recommended that you do the assignment so you can understand this in an easier way. Now, this is the image we have. We're going to run a deep neural network on top. Let's say assignment 6A or 6B or 6, or whichever you're going to pick. And we discussed that this channel has to be. We discussed something about a network, right? What is the size of this channel? Size of the channel?
8 by 8. The final, at least 7 by 7.
At least 7 by 7 or at least 5 cross 5. The worst possible option, but 7 cross 7. We discussed that in last session, right?
Yeah.
The channel has to be big, otherwise you will not be able to run GradCam properly on top. So I have a 7 cross 7 or 5 cross 5 here. What I'm going to do now, forget about this particular guy because he's looking at VGG. What you're going to do, you're going to predict your network. You're going to use the network to predict the class, right? And then you're going to check which class are you going to predict. Basically, which class is there in the image. So I've sent an image. One is going to be high. Okay. I have this image coming in. This goes to my network, and this is the prediction layer. This is going to predict that I have frog. Right? What I'm going to do, I'm going to pick this particular channel, which is just before the prediction layer. Is it clear? And the size of the channel here must be 7 cross 7 or 5 cross 5, which means if you wrote a network in 6A, 6B and something of in those similar sessions, and the channel size is not like 7 cross 7 or 5 cross 5 here, you cannot use that network. So to find a network which I've written where the channel size is 7 cross 7 there or 5 cross 5 there, right? Now if you do that, what are we going to do? We are going to look at the prediction of the network. Let's say the prediction of the network is frog in our case, as we said. We are going to take the channels, right? We're going to take the channels. Then what are we going to do? We're going to calculate for this particular pixel. If I change this particular pixel, what is the change in the prediction? That is going to give me these set of channels. Yes, no? Okay. What is the resolution of this channel we discussed? 7 cross 7. So how many numbers I have here? 49. I'm going to be checking 49 numbers for this particular class, right? And I'm going to rearrange those numbers to get my 7 cross 7 back. So each channel is going to give me its own gradient channel. Is that clear?
These are outputs.
Sorry?
These are outputs.
These are outputs. Yes. Right? Then you're going to be doing what? Doing a gap on top. When you do a gap on top, what are you going to get? You're going to get this channel. Basically one single value. Then we are going to multiply this value with the channels which are coming in. That is going to give us the how important my image is. Let's look at the let's directly look at the code. First let's go through this text and then we'll look at the code. Okay, load the pre-trained model. Right? You cannot do this if the model is not trained. So I've loaded my pre-trained model. Load an image which can be processed by this model, 224 cross 224 for VGG, right? And why do I have to send 224 and 224 only to VGG? Why can't I send 221 and 221? Sorry? Not the correct answer.
So it looks like so it has to inverse the
Yes. We have a fully connected layer. Because you have a fully connected layer, you have fixed the resolution of the input layer. As long as you are using fully connected layer, your resolution fixed before gap, not after gap. If you're using fully connected layer after gap, you can send in any size of image you want. But if it is before gap, then you fix the network because you're going to do the flatten thing. That thing is going to flatten it into some number of neurons. That is the number of neurons your fully connected layer is expecting. So a 7 cross 7 is going to give some different neurons, 11 cross 11 is going to give different neurons. So the network is going to crash, it will just not work. But if you are using our architecture, you can literally send in any size of image. Now load an image, we have loaded an image in a network and processed, and this is processed data we have. Infer the image and get the topmost class. The topmost class happens to be frog for us right now. Compute the gradient of the class output value with respect to the L feature maps. So I have this particular layer. In this layer, I have, let's say, these 32 feature maps, these 32 channels, right? For each particular pixel in this particular in these 32 channels, I'm going to calculate the gradient of my prediction, and this is going to give me these 32 channels back. Right? These are 32 gradient maps now. Is this clear?
How do I calculate the value of the PV prediction?
Is there in the channel? When you predicted my L-1 already has the channel values, you're going to use the channel values.
From 0 to something that it's a value. By what value?
It's a gradient, so you're going to delta change it. So doesn't matter. You're just going to do a derivative. I'm going to show you code also. Is this clear? Right? I've gotten these channels now. What are these channels?
The output of importance.
How do I get this?
By changing the pictures channel.
So apply a gradient of that channel, which is the output of the gradient. Then we do a cache and then.
Anyone else? Okay, this is an important step. See what is happening. This is the layer number L-1. How many channels are inside? 32. After this, we had the softmax and other things, and we predicted a frog here, right? When we say predicted frog, what is this? Essentially some number, 0.932. So I'm going to take one particular channel from here. Let's look at a channel like that. This is the channel I have. I'm not going to draw 7 cross 7. I'm just going to draw 3 cross 3 here. Imagine you're looking at 7 cross 7. I'm going to take this particular pixel, right? And I'm going to do a derivative. Give me the name of this pixel. A. So I'm going to do d this by dA. What is this name of this pixel? V. Then I'm going to do what? D the same number by dB. When I did dA, I got one pixel, one value essentially. Yes? I'm going to get a derivative gradient value. If I now do a derivative with B, I'm going to get another pixel now. If I do with C, I'm going to get another pixel now. So finally I have how many pixels? 7 cross 7? You're seeing a 7 cross 7, right? Wake up. It's not a 3 cross 3. Is it clear? So what is this now? A gradient channel.
But that A is fixed, so how can you like that?
Just ask her to just change for a while. We'll see, I'll show you.
All derivatives are independent of
All derivatives are independent of each other. Very complicated question to ask. All gradients are independent of each other. No, they are not. They are not, because they are output of a single kernel, same kernel. This is backpropagation. This is backpropagation, but we need some channel values also. Is this fine? How we got this channel? So what have we done? We have essentially taken a network. We have sent an image, and this image we are stopping at L-1. We are looking at a prediction of frog, and we are taking every single channel, every single pixel there. We are doing a derivative with respect to. We are doing a derivative of this frog with respect to the channel I have. Then I'm going to create these channels. Right? These are now the gradient channels. This is now we are going to do what? Pool the gradients over all the axes, leaving out the channel dimension. Which means if I had 7 cross 7 cross C here, I'm going to leave the C here and pool over all the other dimensions. Which means I'm going to get what? 1 cross C. Essentially gap. Essentially your gap. You're going to do a gap on the channels I have now. So I'm going to get C values. Weigh the output feature match with respect to the gradients and the positive ones. Which means I'm going to take these channels. I'm going to multiply with all the values if the C happens to be positive. This is clear? If the C happens to be positive, then I'm going to multiply that. By the way, what is the C representing? Okay, what is the 7 cross 7 C? In the 7 cross 7 cross C, what is this 1 7 cross 7 representing? That particular channel. And what is the pixel value representing there? What is the gradient representing? How important is that pixel? Higher the gradient means if you change this a bit, your gradient, your losses, your prediction is going to go small or high. Right? What is the gradient predicting? Essentially this line, right? Or this line, or this line. Basically, what we're saying is that the output is not going to change a lot, even if you change your pixel a lot. That is what we're saying. But if your line looks like this, then even a small variation in your X is going to give you a large variation in your Y. Which means if you change your dA by a small value, this is a small value, this number on top is going to change by a really large number. That means that is how linked it is. So essentially what you're gaining here or what you're getting here you're getting this channel, and on top of this channel you're essentially going to get, okay, this is what you're getting. The values which I'm not drawing, imagine them to be 0, and the values which I'm drawing, they have some value. Now if I do a gap on this, what I'm going to get? Some value, let's say 0.3, right? If that pixel was not important for the output, what is going to happen? The value is going to be negative. If the pixel is not related to the class I'm looking at, then the value is going to be negative, and I'm not taking negative values. So what is this step? Weigh the output feature maps, which means what? I had this network. In this network, I had this layer. On this particular layer, I did my D prediction by D pixel of each channel, right? That gave me these channels. I took these channels and I did a gap. If I did a gap, I got what? C numbers. Yes, I'm going to take these C numbers, which is, let's say, 0.3 minus 0.3, 0.4, and so on, and I'm going to multiply each of these channels with these numbers. This multiplies with this multiplies with this multiplies with this, and so on. I have C channels here and C values here, so I can multiply them, right? Yes, no? Okay, now average the weighted feature maps along the channels. What does it mean? I have these new channels now, these are weighted channels now. I'm going to just average them on the z-axis. I had 7 cross C here. I'm going to convert this into 7 cross 1, right? And I'm going to take this and I'm going to overlay this on top of my image while making sure my values are between 0 and 1, so I can actually view the
What's the positive impact?
Sorry?
If it is negative, if we consider negative,
we consider the positives.
Only positive.
Only positive.
By multiplying.
Yeah. Yeah.
When we take a gradient of that class, the output layer gives probabilities of all the classes. It will be less or negative, but so are we taking for all the probabilities of all the classes? How do you know that this is there or this is a probability of that class?
Oh, you're picking the highest class. You're picking the highest class. Let's look at the code immediately. We have our initialization done. This is the code we are running, and this is the model we have. You have to train your model. Once you train your model, you're going to visualize this. This code is fine. Okay. So this particular file has many different codes. You can look at a particular channel. You can actually look at the kernels also. So if you want to figure out how do I look at the kernel of a particular layer, you can go back and check. But your kernel is going to look like this. It's a 3x3. A kernel 3x3 is going to look like a 3x3, so you cannot expect anything beautiful out of it. What you can do, however, you can use that kernel on top of an image, and that is going to tell you how your image looks like, or what exactly your kernel is extracting. Right? Now you can ask for activations also. Now this is the GradCam implementation. Now what are we doing here? We are loading the VGG function. We are loading VGG. We are loading our image. We are scaling our image to 224 x 3. Right? This has to be the case. Then we are going to use expand dimension to convert image to a batch size 1. Right? Your deep neural networks are trained for batches, and this is one question you're going to find online a lot. You have trained your model and you want to run your model on one image. What should I do? If you go on Stack Overflow, you're going to see this question coming like a million times. I've trained my network, how the hell should I use it? You want to just predict one image. How should I do that?
Use a predict function on the model. That's a
what you're going to see, as long as you're in that notebook, it is fine with you. The moment you take the model out and you use it, you're going to see that you have this extra dimension of the batch. Because batch of size 1. So that is what expand dimension means. Basically, you're going to convert the image into a batch size of 1, which means expand the dimension, add your fourth dimension. Right? You're training your data on. If you've seen your data being trained on, in fact in research papers also, it's going to be space, comma, 224 cross 224 cross 3. That space is the batch size. That is what your network is being trained on. Network is trained on 4 coordinates, not 3. So that is what expand dimension means. Okay, so see what we have done here. We have taken our model, then we are taking our image. We are reading from the internet. You can pick any image you want. We are converting this image to an array. That is what we are going to feed. We're going to expand the dimensions in the x-axis. So we have 4th dimension of the batch, and then we are going to pre-process the input. Now pre-processor is an inbuilt function for VGT, which is going to add that, subtract that mu and divide by the standard deviation. That initial step has to be done. Once you've done that, we are going to predict the model. When we use the model, it's going to predict what class this image is all about.
We are expanding dimension easy estimator or because Keras takes input that. That's the idea.
This is your API dependent. This is API dependent. This is what Keras requires. Now they're going to print the class. It's printing 180. Right? In ImageNet we have 1000 classes. In 1000 classes, predicting the number 180. If you want to know what is number 180, you have to write separate code for that. What are we going to do now? We are going to look at this, class output equal to model.output colon class IDX. What is class IDX? No, class IDX is what? 180. We are asking it to give me the class output. Basically, give me the whole channels. Give me all the channels of this particular class 180. Right? Then we are going to say what? Last conv layer equal to model.get layer block 5 conv 3. So you have to do model.summary. When you do model.summary, that's the name of the layer which is going to be there. You have to find this name, and then I'm copying all of these channels into my last conv layer parameter. Once I've done that, I'm using the grad function, the gradient function. So you're asking it's constant, how can I change it? It's not constant. The output is dependent on that, and there are parameters in between. It's not constant, it's wx into something, right? Because I have a gradient function directly, I can change one of these values, and this is directly inbuilt in Keras, so we don't have to worry about that. What are you doing? You're doing the class outputs, right? What is the class output? What is the class output? Some value, some frog and some other of that sort of value, right? And what is the last conv layer? The last conv layer we just copied. So what we are doing a gradient of a class output with respect to the last layer we have. That is going to give us gradient.shape. I'm printing the shape of the gradient. I just want to see what is the channel I'm getting. Right now I'm getting 14 cross 14 cross 512. What is the next step I'm going to do? I'm going to take a mean of the gradients I have. I'm going to take a mean. We are doing average pooling here. Right? You could have done gap here as well. You can do gap, you can do average pooling, and any other alternative also. Now we have VGT network. VG network at that layer has 502 channels. Then we are iterating. Okay, what are we doing here? Iterate k function model input. Essentially, this is us multiplying the C values with the C channels coming in. So I have those 512 values. I'm multiplying the 512 channels with these 512 values. For I equal to range, and what are we doing here? We are summing those channels now. I'm summing all those 512 channels to get one single channel. Now, if I do that, I'm going to get my heat map. I'm going to get a mean again because I need to have my values between 0 and 1. Once I've done that, I'm getting a 14 cross 14. After this is the dog I have, and if I overlay my heat map on top, this is the kind of heat map you're going to get. Some things are in OpenCV here, some things are in NumPy, so you're going to suffer some of the problems in this particular algorithm when you go back and implement. Right? You need to make sure that everything is understood by you what you're doing. OpenCV handles BGR, not RGB, so that conversion has to be taken care. And by the way, we printed a 14 cross 14 image here. This is not a RGB. 14 cross 14 is just a gray image. But you're still getting colors here. Why is that? Because you're using something called heat map. Right? How does a heat map look like?
Model.input is the entire model of the layer of last layer.
1 second. These are many different kind of heat maps which are available. These are called color maps. You can pick either of them. Which one are we using? We are using color map jet. What is color map jet? This is color map jet. So it's going to say this blue is 0 and this red is white. This red is 1. So any value in between, you have a color now. You're just going to go in this particular range, pick that color and paste it on top of the image. We had a question here.
When we say model.input.
Model.input. We've done model.input here?
Below.
Here, okay.
Model.input.
Model.input. Okay. Okay.
This is the entire model is the last layer. And what is this input?
What is this input? For which model are we talking about?
We create our own model. And when we're deploying it and it's a model or input, it will take the entire model.
Entire model with the input you have sent. This is with respect to the image you have, right?
The model is trained for the entire images. So when you say model input, it is going to take the entire model here?
Entire model. Alright, so this is the GradCam algorithm. It's very easy to implement, and the next step for you is to understand DevConNet, but I think we are short on time today. So I'll cover this part in the next session. It's a very small part anyway, so we don't have to worry about that. Okay, what is your assignment now is that this is one part I need to cover. I'll cover in the next session. Okay, so we are losing 15 minutes today. Okay, refer the GradCam code, the code which I have shared. Build the GradCam images from one layer before the one we have used, right, and the one layer after this one. Show the results. What are we doing here? Refer to the GradCam we wrote. Refer to the GradCam code we are seeing. Build GradCam images for the layer before this and after this. Is that correct? What are you going to do? You're going to. I have picked I picked a specific one. You need to see that what is the layer I have picked one, and do we have a layer after this? If yes, then you have to do GradCam for that layer, and you have to do a GradCam for. You need to go to model summary and figure out where is this. There's a layer before this and a layer after that. You're going to say implement. How do you know? So you need to see what you can do there.
I'm clear about the statement of the assignment.
What is the question?
The assignment is for the one layer before the one we use and one layer before this one. Okay, so 2 layers before the one that we use.
Yes.
Right. Nothing after that.
Yeah. Show the result. So you're going to show the result of the GradCam before the L-1 and L-2. Load the image. You're going to load this particular image. Okay, and in this particular image, find sunglasses. What is the question? You're going to use the VGG network. You're going to load this image in the VGG, and you're going to find the sunglasses. How are you going to find the sunglasses? Sunglasses is there as one of the classes in VGG, in the ImbisNet. So what are you going to do? Your class IDX, which was 180, you're going to find what is the sunglass. For that class, you're going to do the gradient. Right? And please follow what I've just shared you. If you follow this particular procedure, you're going to learn that in an image you can find any object. If you just apply this, take this particular image and run through VGT, you're going to see it already predicts sunglasses. So if you don't change anything, the assignment still remains the same. But you have not done the assignment. What is the assignment?
You change the layer.
No, assignment is to go back, check ImageNet, figure out what is the class number for sunglasses and do a gradient directly for that. That is assignment. If you do that, then you'll actually get to know how can you find any other image. Is this clear? Okay. Now, the second part, refer to this particular table. Yeah, you don't have to do this. Second, I'll remove. It's in EVA 1 also not many got this. Yeah, so you only have one assignment because you have not done the last assignment also. Please submit the last assignment. Any question on the assignment? Yes, no? Okay, so we are missing some components here. Next time we are going to start 6:30 sharp, so we get to cover these parts also. Alright, have a very good day.